our lessons today is beam deflections and use superposition to determine the beam deflection and also solve the indeterminate beams. And the chapter is chapter 9, and this in front of you is study guide. And in the study guide we give you a review that we learn about the curvature in the calculus with many good information and equation derived from the calculus. Example, this is one, and also with that transformation at the end we have one row equal to second derivative of y over dx and 1 plus dy over dx square root of 3 power 3 over 2 1/2, and rho in this case is the radius of the curvature. So that I will get back to that when we get to the lesson, but keep in mind this is something you learn from calculus, and we will going to utilize that for today's lesson when we study elastic curve for the deflection. So let's go to here. We have the definition of elastic curve. Elastic curve. What is that about? If we have let's make a simple beam here and assume the pin at one end and the roller at the other end, and we have a distributed load, uniform distributed load throughout this beam, and let's cause that is W. And as you can see, when we have that load, the beam will be deformed, and that deform in that load here. With that load going down, then the beam, and I exaggerate the deformation because normally we deal with in a small, very small, very little deformation for the real structure. And let me call the axis along the longitudinal axis of the beam, that is x, that's nothing new, and the vertical axis is y. The vertical axis is y, and we start from the origins is from the left of the beam, as you can see there. So what is the definition of elastic curve for here? So definition, let me put it out, sketch, and I just sketch the dash line in there. So the sketch of the deflected shape of the beam, which show the displacement of the beam. The beam which show the displacement of the beam. And that is the definition of the elastic curve. If we relieve the load, then because it's elastic, then the beam will return to the original shape. And the way that deflect and the associated elastic curve, it will depend on the support condition, pins, fixed support, etc. So let's put it out. It also depends on support condition. So let me elaborate some support condition that you may see in these scenarios. So support condition, and there are typical support condition that we deal in this class. The first, as you can see, the roller at one end. So if I have a beam here and just draw a portion of the beam here, and if we have a roller at A at one end, then what do you have? When it roller, the beam will not going down at that point. So you have the delta. You will have delta, or also equal to the y, based on our definition of y is the vertical deflection here. So the ya at point A equal to 0. But it will deflect in terms of the angles. The angle of the deflections may go down like this for the beam, and the angle theta here, that one at that point. So that the theta that you can see here, it will be not 0. And in this case, as you can see, theta A is non-zero. And at the pins, we already know moment at that point equal to 0 because the roller, but the vertical reactions is also not 0. Vertical reaction are not 0 because we have a AY in the statics that you have that. So basically, if we have a roller at one end, so the delta, it will be 0. The angle of the deflection will be non-zero, moment 0, and then shear or the vertical load, the vertical reaction at A, it will be non-zero. That's nothing new in here. So if the second scenario, if we have a beam, I might just show part of that, and instead of roller at A, I replace with the pins. So let's write down here. The first one is roller at N. What do we have? The support condition on the right, and then we have pin at N. What do we have? Exactly the same with the roller. The angle will be changed, but not the vertical deflection. So I can say same at above. At roller. Meaning that delta equal to 0, theta is non-zero, moment is 0, and vertical reactions at A is non-zero. The other support condition that you see a lot is the fixed end. Fixed end. So if we have a beam, part of the beam, and then at A we have a fixed support at A. So what do we have in this case? As you can see, at fixed, so it's just about A, the angles will be 0. It's not changing at point A instead of the angle of deflection. Also vertical deflection, because that is fixed. So what we have here is YA for the fixed end. We have YA, and that also delta that the book says. So delta, which is the vertical deflection at that point A, is 0, and then the theta A at point A also 0 for the fixed end. So that's different from roller or pin where theta is non-zero, as you can see that. And then of course fixed support we have MA is non-zero, and vertical reaction at A is non-zero. So that is the support condition that you will see in there. Other condition that we have, so roller, pin at end, fixed end, the continue. We have the support condition continue here. Support condition. Support condition. Let's continue with that. The scenarios that I want to continue is the free end. So no support at all, free end. So part of the beam in here. So no thin support. So as you can see at that point, it can deflect. So when it no support, what do we have? We have the delta equal to the free end, I call that A, point A. So equal to YA, and it non-zero for sure. And theta A also non-zero. And for free, if it no couple applied, then it will be 0, and the reaction VA equals 0 if no load applied on that point. And then we have internal roller or pins. What happened when we have internal roller or pins? Internal, it means in the middle of the beam. Here we have a roller or a pins. What do we have? Then, as you can see, depends on the load on the left or the right, the angle of deflection can go left, go right, or both. So with that, what do we have? At the roller at one end, we have delta at that point A, delta equal to the vertical deflection at point A is 0, right? With the roller support, nothing. Theta, of course, theta A is equal to non-zero. Moment, also non-zero, and of course VA equal to non-zero. So that is the fifth support condition we are talking about. So let's talk about the last one, is the hinge. What if we have a hinge? So we have the hinge connect the two members. The hinge here. So it means that they be able to freely rotate each other. So what do we have for the hinge? As you can see, hinge, then it can be both sides freely to rotate. So the theta, it cannot be the same for in one side and the other side. So what do we have here? The delta, and that is A equal to YA, vertical at A, of course, is non-zero because it can go down, nothing for the hinge. And then, of course, we have a theta in both sides. So let me define here, that is theta 1 and theta 2. So what we have here, we have theta 1. It's not the same as theta 2 for the hinge, and of course is non-zero. And of course we have for the hinge, it's freely to move, so moment at point A equal to 0. And also the reaction force, vertical reaction force is also non-zero. So that are the support condition for that elastic curve will be depend on. And the next video I will show you the some examples, and then we derive the relationship between the moment and the elastic curve functions.